Hello, good evening all the participants. So I welcome you all here in the third day, session 2 of FDP on deep learning. Now today Professor Rajesh sir is with us. So I welcome Professor Rajesh sir. Thank you sir for being with us now today. Hello, sir, is my voice audible to you?
Yeah, thank you, Dr. Surinder. I can hear you.
Thank you sir. So before start this session, let me introduce Professor Rajesh sir. Professor Rajesh Kumar received the B.Tech degree in electrical engineering from the National Institute of Technology, Kurukshetra in 1994. The ME and PhD degree in Power System and Intelligent System from the Malvi National Institute of Technology, Jaipur in 1997 and 2005. He was a postdoctoral research fellow with the Department of Electrical and Computer Engineering, National University of Singapore from 2009 to 2011. Currently, he is working as a professor of artificial intelligence at the Department of Human Anatomy and Physiology, Faculty of Health Science, University of Johannesburg, South Africa, and a professor in the Department of Electrical Engineering, MNIT Jaipur. His research interests focus on intelligent systems, data-driven algorithms, computational neuroscience, energy, and healthcare. He holds 20 patents, patent applications, and has published over 750 research articles in international conferences and journals. He has supervised 28 PhD and more than 60 master's theses. He has received the several academic best paper, best thesis, and professional awards. He was felicitated with the Career Award for Young Teachers in 2002 by the Government of India. He has delivered over 350 keynotes, expert talks at conferences, faculty development programs, and workshops. He has been on the research boards of more than 30 universities worldwide. He is also on the board of studies of 20 universities in India. He has also worked as an accreditation evaluator for NBA, NAC, and AICT. He was conference program chair, PADES 2018, general co-chair of many conferences. He has been an associate editor of IEEE Access, many IEEE transactions, IET, international journals of bio-inspired computing, and many more IEEE transactions journal. He has been an IEEE counselor, MNIT student branch founding faculty advisor, IEEE IES student chapter at MNIT, honorary secretary IET Rajasthan chapter, XCOM IEEE Delhi PES and vice chairman IEEE Rajasthan subsection. He is an IEEE IS distinguished lecturer 2024 to 2025, and many more. So thank you, sir. Thank you for being with us today.
Uh, Thank you, Dr. Surinder, for a detailed introduction. I hope I'm audible and fine to everyone.
Yes, sir. Audible, sir. And your screen is
My
also
screen
visible.
is
Yes,
okay.
yes.
Okay, thank you. Thank you very much, and yeah, good afternoon to all the members who joined here, my colleagues and uh, young researchers. Today, today we will talk about a very important aspect of AI, and that is basically the explainable AI. We want to see like the models which we are using or the AI modules which we are developing, algorithms which we are developing, are they explainable? So during this lecture, we start with just start with the understanding of the thing, AI, and then what people are talking about, why this, how this is growing area, and then we talk about the some approaches which we can use to make people understand that why this model is taking this decision, and then later on we'll discuss some case studies. Just 1 second. Okay, so people keep on comparing the two intelligences, basically human versus machine intelligence, and then they compare it on various parameters. Like when we talk about the energy efficiency, so usually our brain consumes 25 watts. Machine intelligence, don't get it confused, like it's a 2 watt for a 2 watts is if I take a 20,000 data points and there are only two features. Then it comes to what, but we know that most of the processings we do it, we consume a lot of power there. Universal accept thought process. If we talk about learning, we talk about uh, then in learning, humans usually learn how to manage hundreds of different of skills during the whole lifetime. But when we talk about the machines, they are designed for certain tasks. They are not like a kind of a universal stuff that keep on learning different aspects. They are designed for to perform a certain one aspect of it. The new research is moving in that direction. Can we design the algorithms where we can think of multiple aspects and all that? If you talk about the processing, you can see there the brain usually process around, you can see, 1000 k trillion operations per second, whereas your computers or your machines, they usually take 93 k trillion operations per second. We also know that our multitasking, we are good as a humans. Machines, we are in a process to develop multitasking. Space we know, and the weight also we know that if you compare the human intelligence with the machine intelligence, there is a lot of variations in there. And the another thing which is still so far, our brain is analog machine, whereas the machines which we are using, the computers or the codes, they are most of them are digital, and people are looking how can we make it close to the human intelligence and all that. And the journey is almost now it's more than some can say 75 years now or so. It started with 1950 when the first like Turing test by Alan Turing came into picture, and then the term AI was coined in 56, and then the developments are there. There was a period from 71 to 1990 where the winter appears. That means the downfall. There are means downfall, or you can say the rate of progress is slow, but it again picked up in 97 when Deep Blue defeated chess champion. Gary Kasparov was one of the popular chess player, and then when it beat it again, it start picking that direction, and then people come out with emotional intelligence, and then robotics comes into the picture. So that again boost it up, and then later on you can see that in 2010 beyond, there is a big change, and last 10 years there's a drastic change. Now it's a acceptable, it's a proven technology. You'll find the applications everywhere. Even like in today's modern world, we can't think of any processing without some or direct or indirect form of AI into it. People talk about various domains. They talk about AI, they talk about machine learning, talk about deep learning, and so on. Well, AI is basically the overall structure when we talk about the advanced technology, just to mimic the human intelligence, that how the intelligence can be structurized or can be converted into some kind of algorithm or mathematical form to solve some problem. Machine learning is a subset of it. So it learns from certain kind of patterns, and then deep learning is basically another subset of machine learning, which is more focused towards neural networks and the use of neural networks in a big way. So this is how the terms they keep on coming up, and then people keep on using these terms interchangeably. Like machine learning, they say sometimes they say by when they are talking about like machine learning with the put LSTM in machine learning, but it is a subset of it. And then people say, no, it's a deep learning. So don't get it confused over these terminologies which are being used there. So this is a conceptual picture, and most of us, those who are here in this session, we are aware of these things, that what is human intelligence and how the machine intelligence comes into the picture. So we have certain. So what is or question is, what is a traditional programming? So this is a concept picture, but you can take it in mathematical form that, okay, what I'll do is I know what is X, and then I write down a code that Y is 2 of X, and then I run a program, and then the program give me the output that, okay, if X is 2, then Y is 4. This is a traditional programming. Whereas in machine learning, what we are looking is we give X and value of X, that is 2, and the value of Y as 4, and then we ask the machine to develop a model for us which connect X with Y. That is actually what is we are looking for, and that you'll find that we call as a model also. And then the model can be a light model, or it can be a big model or deep model or something like that. So this picture is very common. You just search at Google, you'll find this picture there, and you can see there are a lot of branches now. They are coming out of these things. So this one is from a machine learning, but I told you machine learning is a subset of AI. AI has more things. There are a lot of things which are not there. Things like fuzzy network, things like data mapping, theory of brain, thinking process, and a lot of things are there. Machine learning is more on the data and the learning from the patterns, and likewise. And then in machine learning, we have so many things like ANN and RL and classical and ensemble, and then all these have again bifurcated into some many more small segments there. And all these are the different algorithms which are nowadays very popular. Well, now the people are moving towards deep learning, and then the question is again, what is there in deep learning? Why deep learning is so attractive? The point is, in machine learning, we have some data, but before sending it to some kind of models, we do certain kind of feature engineering. And once we process it, when we do, after doing the feature engineering, we send those data to some models, and then train those models, and then evaluate those models. But the important part is the feature engineering here, and feature engineering varies. If I'm an expert of that particular domain, then I can extract good features and my model will be good. But if I'm not aware of that, like some of us who are here may not be that good of medical science, but they are handling medical data. But there is another guy who is good in medical science. So then what he can do from that data, he can do some kind of a feature engineering, and then take some kind of meaningful and good data and then train the model. So it depends upon the person who is doing that feature engineering part, or the mathematical equations or models which we are using to do the feature engineering. Whereas to make it more automated, people thought of another approach, and the mathematicians jumped into it, and they added that why not to make the models in such a way that the feature engineering will be also done by the models itself. And there comes the deep learning. So if you see the deep learning models, first few layers, so this one is a neural network. Yeah, everybody is aware of it. Let me take so this one is a deep means it's more in the depth. The first few layers, they do certain kind of feature engineering. Last layers, they do a certain kind of identifications, classifications, or regressions kind of. So that's how these things are transformed from one level to the another level. And when we compare it, the comparison again, we can compare under two aspects. If we say machine learning models, they can be trained on less data because we do some feature engineering already. But since in deep learning we are we want the model, it's also model to do the job of feature engineering, we'll need a large data, lot of data are there. And yeah, as I told you, it depends upon the feature engineering models which we are using, so that affects the accuracy. Deep learning has a relatively higher accuracy because they are working on lot of data, as well as the models which are used in deep learning, they are very deep. And then the operations which we use in deep learning, uh, we use all the aspects there, like how to remove the biasness, how to remove all those aspects there. We add to it so that we can have better models. And likewise, obviously the data is high, they take a lot of time, they need a high computing facilities, and the hyperparameters you can tune in various ways. So those are the comparison between deep learning and machine learning. And this is one of the study reports from Stanford. It's old, not new, but you can see the publications in the area of the, AI and on this domain. You can see that it's a spiking there. Publications, if we go by the number of the AI publications, you can see the pattern recognition, how it jumps from, it's almost doubled in last 10 years. This is still 21, but last 5 years, this again, you will find a lot of growth is there. And then the patents also, you can see almost 10 in 2010, almost nil patent. But if you can see the patents somewhere in 2021, it's it's somewhere around 14,000. But if you go by 2025, it crosses 20,000 and beyond that. Okay, and then if you see the AI skills penetrations country-wise, this is very important. And this is very important for we Indians also here. The reason is the penetration of this domain, this technology. If you compare with other countries, it's a very large. You check about the education, finance, hardware, software, and manufacturing also. The penetration is very high, and that's why it's very important for us to look into these things, or to understand these things in uh, much in depth, so that we can address, or we can develop something more into it. So applications are full of it. You start with healthcare, automobile, finance, surveillance, social media, agriculture, e-commerce, robotics, gaming, educations, space explorations, and many more. And there are pros and cons, and people are debating over these things. What are the pros and cons of AI? And if we have issues, then we talk about how to how to address those issues. Say cons, it needs a high cost. So then now people are working in the domain that how we can make our models light. How can we make our models deployable on a simple segments? Or how can we make our model so light that you can train it on some small machine source? Another cons, we talk about ethical consideration. So now the ethical AI, explainable AI, and all these things are coming into the picture. So we know that these are the these are the cons, and then now we are working towards that how we can address these cons, which are cons related to AI. And to meet these things, so I'm start taking the last part, that is ethical considerations and all these things, make it more meaningful. This AI, the new area is developing, and that is basically explainable AI. So you can see the earlier AI is we take a data and then we have black box model, and then that model gives certain output, and then humans they use those models there. But what is an explainable AI? One another layer is introduced. So we have data, and then we have the black box, which gives certain output, and then we use another approach over it, another mathematical operations over it, which give the humans the information that why why this decision is taken, why this value comes out of it. Because okay, you are training something and you have data and you are doing a classification, and then outcome of your model is say it's a tumor. But the next point is that is basically why this decision comes into the picture, and that is basically the that query uh, put the researchers to work on the things that what are those parameters which dominate or which helps in taking this decision, and so that one can explain that why the decision is being taken. And this is a taken from a research article which is on XAI. You can see here what we are looking for is, okay, we have certain data, we have some learning process, functions, and then there is an output that this picture is the uh, picture of cat with a probability of 93%. But then the user has various questions, and the questions are these are obvious questions that why did you do that, means like how you are getting it, why not something else, why you are saying this picture is a cat, how you succeed in that one. And the important part is when do you fail? And this is very important. You will find some research article, people are working on some complex pictures which look like similar, so that if you push it and they try to find out when this my model will fail, when can I trust you, and then if there is error, how do I correct the error if it is there? Because we know that accuracy we are achieving 99%, so there is an error of 1%. Well, if you are working with health science, then 1% is very big error. But then the question is why this 1%, and then if I want to correct it, how I can correct it. So this explainable AI is basically you put another thing in between which explain the model, okay, which explain it that like this picture, when I my model as a model, when I consider this picture, I check out that it has fur, it has clothes, it's whiskers, and from there can I answer these things that like why I've taken this decision. So user can understand that why you have taken this, why the model has given this answer, when it can fail, and then how you can trust over it. And that is basically explainable AI. So it is essential for a user to understand and the trust, and then the effectively manage the incoming informations and all those things there. And that's how this area is being developed, which is known as a explainable AI. So the concept is basically we need to work on the things, what are the decisions, basically what are the recommendations. So what is the target of XAI? It target the decisions, it target the recommendations, it target about the understanding the rationale of the decisions being taken to answer all those queries which are raised by the users, and that make it a trustworthy also. Because say uh, some data is some data, somebody applied for a loan, and then they ask for some data, and the person provide the data, and then they reject the loan. Then person claim on it that why you have rejected. So you cannot say that the model has given that that it's this denial, uh, classify and put the person into the denial group. But then the person will ask why I'm attached with, or I'm placed in that group, which is a denial group. So it has to be answerable in that way. Okay. So we talk about the things there, and what are the three things which are required. One is explainable model, the models which can explain. Then how it is the machine learn, how it is developing the model. Explanation on the inference, how you are inferring the things, and what is the psychology of explanation, that how those things can be taken further. So it's more towards developing a computational theory and likewise. So theory of XAI is basically history. If you talk about before going to the theory, it started somewhere in 56. People start talking about this thing, and then when the first wave appears or AI appears, then they try to mimic the decision making and all those things. But the actual work and those things comes later on, when you can see in 2010 somewhere that AI is introduced, and then after there are certain improvements, new models comes into the picture, so that we can understand how the models are taking a decision. So there are three main key pillars of explainable AI. One is whether my AI is reasonable or not. So reasonable AI means the ability to understand the reasoning behind each individual predictions. So reasonable AI is independent segment, but some part of reasonable AI that is attached to the explainable AI. The second part is understandable AI, that the ability that how the decision making is being done, and then the another part is that is a traceable AI. So from the logic of mathematics and all that, do we have a traces of your prediction process and all that. So these are the principles of explainable AI. The designing part with AI as a societal impact, then defining the things, some standards, testing the things because before the release, we check it, then we use it. We need some kind of a transparency in that one, and then monitor it after the AI model is released, and then fostering it, protecting it, and then establishing the things there. This is a very interesting graph which can give us two things. On one axis, it's accuracy. On another axis, it is the explainability and interpretability. You just check it out. Those models which are simple classification rules, which are decision trees, they are very light models. And then there is a simple explanation there that if X is more than this, then you are in this category, and if X is less than this, you are in this category. So there is a clear-cut explanation that since your X value is this much, you belong to A category. Next person, your X value is this much, you belong to B category. So they are explainable. But then when you check it on the accuracy side, the accuracy is low. So if you look for a higher accuracy, you have to go for a complex models, like we start from dysentery, k-nearest, and then support vector, random forest, neural network. The accuracy keep on increasing, but at the same time, your explainability part keep on reducing. So the high accurate models, they have a nonlinear relationships. We all know that they have nonlinear. Uh, uh, they use nonlinear smoothing functions. The time of computation is high, whereas the high interpretable models, they are linear, they are very smooth. The relationship is straightforward. They are easy to compute. So now there is a conflict here, accuracy versus these things. We all know that we need accuracy, high accuracy, but we at the same time we also want that the models can be more explainable, and that is basically what we do in explainable AI. So these are the pictures taken from the research article. The same, I forget to mention here the reference of that one, but you can see which model is lying here. So you can see here the red models, they are high, they have a very high accuracy, but at the same time they have a poor explainability part there. Okay, so those things we need to check it out. You go for the complexity, accuracy keep on increasing, but the explanation part keep on reducing. What is the way? What is the way to get it done? So we categorize the XAI. People have done a lot of XAI model, and we can categorize them. So that is basically one category is model agnostic. That means the approach can be applicable to any model. whether your model is decision tree or neural network or what type, it can be applied to any model. It's a model free kind. Those there are approaches which are model agnostic. There are approaches which are model specific also. We'll discuss in coming slides these approaches. And then we are looking for a global explanation which explain the whole model, or we are looking for a local explanation that okay explains some kind of a local area and all that. They can be categorized post ad hoc, that is analyze the model after training. They can be intrinsic, that means they explain the model in between also. And then explainable types, how you want to or which type you want, whether you want them to explain visually or feature wise, feature importance, or some text, or some kind of a surrogate model. So you can divide or categorize your explainable AI models in these four categories: agnosticity, scopes, explainable type, and then post ad hoc or not. So let's start with model agnostic techniques. These are basically model free techniques. Basically, you can apply to the different models. Okay, yeah, okay, here the reference is given. These are given. So these are the basically the distribution on house prices, a very popular problem. If you are working the AI, people work a lot on house pricing problem and solved by MLP. And then we try to find it out that what is the explainable, how we can explain it. So people do one way is you do the sensitivity analysis. Okay, and then from the sensitivity analysis, then you can find out that some dependencies and then use those dependency features to explain that whether it's this why this value is appearing there. So we look for more on the dependency plots. So there is one variable and then another variable, and we take a lot of data and make the patches and then try to show the dependency on each other, and then we can use some statistical approach to give some numbers that how much is they are strongly related on the dependencies on each other, and then try to find out the answer. This one is a popular approach, but what is the problem in this earlier approach is basically if you have large number of the data points or features, then it create a problem. Then the dependency part, then the plots and the analysis, sensitive analysis is it become very complex. So if the variables are very less, we can easily perform the sensitivity analysis and then the dependencies and all that, but the number of the variables are more than it create a problem there. This one is a popular approach which is known as LIME, local interpretable model explanation. That means we use an approach and that we apply over a black box model so that we can have some kind of explanation. So it's an approximate approach, and what it do is basically it try to find out the importance of the feature. So there are various ways to find out the importance. So importance of feature, you can do it by correlation and covariance analysis and all that. The another part of it is let the model to predict something, and then what we can do is we can perturb the input data somewhere, and then we check it out what is the effect of that perturbation on the model output, and from there we can make a judgment and we can put a certain kind of weightage or evaluation that how important is that feature, and that will help us later on deciding that why the decision is being taken. Let's understand in depth here. So like this is these are the two features, F1 and F2. These are the two features here. Okay, now we are going at a good speed. So so you can see here there are light blue and the dark blue. So dark blue is basically stroke and light is not no stroke. And now you can see that if I see this pattern, this is not a linearly separable, it's a complex pattern. Okay, so we need a complex model to separate dark blue with the light blue. That means stroke, no stroke, based upon these two features. Okay. So let's say we use a neural network which give you a good approximation, and then the neural network, the decision boundary of neural network is like this, which you can see on your screen. Okay, which you can see here. So you have uh, you have light blue on one side and dark blue on another side. This is the decision boundary. But the question is now the question comes in, because when you take a new point anywhere, so if it is on the inside the decision boundary, you will say no stroke, and you will inside, if it is outside the boundary, you'll say it's a stroke. So if I take a point here somewhere, I'll say that now feature based, because this point is very simple, because here only the feature one is 0, only feature 2 exists. So I can say that because of the feature 2, this is the decision. Okay, but there's some other point where the feature 1 is also there, and feature 2 is though you can see the feature 2 is increased at, if I see this point, but feature 1 is also there, and the decision is again it's a no, it's a stroke. So now it's a difficult difficult for a person to say, and obviously as a user or consumer, person will ask, why this shape of the boundary, why not some other shape? And that's where we use LIME approach, which is local interpretable model explanation. That means we will interpret the model locally. So what we do is we perturb some of the one point here. So we shift this point from here to the red one. You can see the red point here. And in this area only, we use this one. This one you can see here. What is this? This is a straight line. Straight line means it's a kind of a simple decision tree, or it's a linear boundary. We know that linear boundary can be easily explainable. So we perturb this blue to a red one, and then check it that how that perturbation make a change. So if I perturb with certain amount, certain degree, and still it's the same, I can give a certain kind of a confidence. And if I go beyond it, then I have a certain kind of other information, and likewise. Okay, so what we are looking for, so how you perturb it. So what we can do is, this is the basically the approach which the people have used. So they go for surrogate model training, and what they do in surrogate modeling is basically they perturb it by the perturb, but you can see the distribution is there. They use a Gaussian distribution kind of stuff there, so that the perturbation is according to the magnitude, and then this perturbation will give us a different level of the classification on this side and on this side. So we are looking for this kind of equation. I'll show you one example that how it is working. But we have a loss function which is here. So one of them is, this one is the good approximation, and another one is a more simple model. And what we are looking for is, we want to check it that how we can make complex model. Yeah, so okay, what does perturbation means? I'll explain you. Perturbation means this is the actual, you can see on your screen, this blue point is the actual point, and I move this point from here to here. That means I change some values of the feature 1 and feature 2, so that this point change from this to this, so that we can understand that if this change is there, whether this new point is on left side of the decision boundary or on the right side of the decision boundary. So you can see all these brown points, these are the perturbed points of this actual one is this blue one. So how long it will give us the correct one, correct answer. You can see if I go beyond these lines, I have some wrong answers also. Wrong answers means the classification changes. That is the meaning here. So what is the goal is, what we are looking for is, we are looking locally. Locally means in a very small region. that how we can approximate a complex model to a simple model. Because if my model is simple, I know I can easily explain it why it is happening. But if my model is complex, I cannot explain it. So we do it locally in various zones to explain the things, and that is the theme of this work. Let's take this example. You can understand from here. Okay, so we can take here we'll do try to check 2 examples. We can take more also. Okay, so what is the flow? So first is pick a prediction to explain. Like, okay, that is what what I told you, the perturb point. So you choose any point that if I why this point which is appearing here is spam or not spam, or stroke no stroke, and likewise. And then we perturb this point. Okay, and then from the new point we get the predictions, and then we assign weight to this one, and then we train the simple model on those perturbed samples, and then we interpret it. Let's go one by one. Say this is a simple example. Okay, so we have a black box classifier which is fx. I don't know what is that classifier, but that predicts whether a person will buy a product, one, or and not if, and that is it is 0. And there are only 2 features which are input to my model: x1 age, x2 is the salary. So now my setup is the inputs to my model, there are 2 features, age and salary, and the output of my model, machine learning model, is 1 or 0. 1, the person will buy a product; 0, not well, the person will not buy. Okay, so this is my model. Okay, if they buy, and 0 if they don't buy. Now let's say the input comes like this. Yeah, I will discuss more. You keep the things so that we can discuss the things at the end. So the explanation part, this is a very common example you'll find every where I put it here just to have a discussion on it. So suppose we have 2 values comes in here. One is the 30, that is the age, and the salary is 70K, and the value is 1. That means my model is saying that this person of 30 years of age with the 70,000 salary will buy. And then the question is, why this decision? Why not 0? Okay, so now we go for it. So the first step is perturb the input. So what we'll do, we perturb the inputs, small change. Okay, and we generate some samples, adding some noise to it. Okay, so these are the samples which are generated here. We have variations in x, both sides. If it was 30, we make it 32, 28, 40, 10, 30, and likewise. We have some salary also, and we have certain kind of fx, that's the kind of a predictions, and from there. And then we weight the samples. So samples we weight by this distribution. Computer science, we call it the kernel function. So this one is a, we know these values there, because these things will help us in making a decision. So we assume that, okay, sigma is 10. We know what is sigma in this model. This is a very common equation of machine we use in machine learning. So we calculate the distance from the x, that is the new point. What is the distance of new point with the old point? So we know the distance formula. There are various distance methods, so you can use it. This one is a simple equivalent distance way. We can calculate what is the weight here. You can see the weight is also assigned here. Okay, so this is the part 2, and then we use a simple linear model to fit it. So what is my linear model? Two inputs. So W1 or first input plus W2 or second part plus B, likewise. So we have W1 and so what over the new data which we have, what we do is we train a simple weighted linear regression. So we will get this equation. This equation, we have two coefficients appear here, this one and this one. Now they will tell us, that's the interpretation, that age has a 0.03%, 0.03 weightage. So how it is contributing, and the salary has this much of weightage, and how it is contributing. So in overall, we can say that age has more influence than the salary. This is how you can interpret the model. This is how the working takes place. You can take another example. This one is also available on you can search it on Google. It is also there, like sentiment classification, a common problem in computer science. So we give a text and then we say that it's a positive sentiment or it's a negative sentiment. So in sentence is like this: I absolutely love the movie. It was brilliant and inspiring. And say this one is a positive sentiment. So we follow the again same thing. We perturb the input. So that means we create many perturbed text like this. And then we have fx value. We use kernel. Here the kernel is different because of the text part. We use hot encodings some way. And then we find out the weight. And then over this new data or this created data, we sampled we develop a weighted linear model. So linear model is what is it is there the sentence, you know we have words, so we have loud and the brilliant and the inspiring and all these things. What are the weight to it? Once you fit your linear model over this thing, you will find some value of W1, W2, W3 and likewise. And let's say W2 is the getting a highest weightage, so that means that means the brilliant word is affecting my output in a bigger way rather than the other words and likewise. So we have some kind of explanation why the model is taking that kind of a decision. Okay, so this is how you can interpret it. Okay, so I hope Lime is a bit clear to you. Let's move to the another approach, and which is again, this is also model agnostic techniques. This is basically known as SHAP. It is Shapley additive explanations inspired from management side, the game theory. And the point is, and this is basically the concept picture which I put it here. You can see that how it works. And the work is very simple. These three people, they combine and went to a restaurant, and there is a bill amount, and then there's a payment basically. So it's a game theory in a way that what we can do is some amount is billed, and then who is contributing how much. So the thing is basically we start it in a way, and this is basically you can take it like this, that ABC are the features, and this is the model which is giving a certain kind of output. And to us, we need to understand which feature is more important. The approach is very simple here. You can see here we take only we check the case when only A is there, then we check the case only B is there, then we check the case only C is there. This is the simplest way. You take a model, you give only A input, make others 0, what is the performance? Then you give B, make others 0, what is the performance? Give C, what is the performance? Then give A and B, what is the performance? And likewise. So we have all possible combinations, and from there we can find out that what is the contribution of that particular feature in getting the answer. This is basically known as SHAP. Okay, so SHAP equation, you will find common equation like this. Okay, we have these values. This one is Shapley value, this one is black box model, these are the inputs, these are the total number of features. So we go for the weighing process, and we have a contribution process. Let's check it with an example. Very simple example I'm taking here, that okay, if we have a model that returns a score, of loan approval 0 and 1, and 3 binary features. Okay, X has stable job 1, yes, 0, no. Similarly, X2 good score 1 and 0. Okay, and 3 has a collateral. So we have this matrix. Okay, 0 0 0, we have some fx value, we have 1 0 0, we have some effect. So for each input we check it, that if only x all are zeros, what will be the fx? If only 1 is there, that means only x1 feature is there, what is the value? Only x2 feature is there, what is the value? Only x3 feature is there, what is the value? Both x1 x2 are there, what is the value? X1 x3 are there, what is the value? X2 x3, what is the value? And if all the 3 are there, what is the value there? And then if the prediction is this, now let's come to that part. So if I give input 111, a prediction is 0.9, we can easily calculate phi values and all those things. How we calculate it? Okay, phi, if this is the score, phi x1 means only first feature, and null means if it is not there. Okay, and then we calculate it for x2, we calculate it for x3, and then x2 x3, and then we calculate the weighted average of it, and we do it for all the things, and then the average value will give us the solution here. Similarly, we calculate for feature x2, we calculate it for feature x3. We will have all these values because 0 0 is baseline. So when you add to it x0 x1 plus x2 plus x3, that will be the prediction. That means if baseline plus contribution of first feature plus contribution of the second feature and plus contribution of third feature, if you sum all the 3, you will get the answer, which is 0.92, which is otherwise 0.9. So 0.92 is, that is basically a score near around it. So the process is very simple. We individually put the features one by one, and then we evaluate the performance, and the final solution will be the baseline, that is everything is 0 plus, then we keep on the score obtained by average score obtained by the first feature, average impact by second, average impact by third, because here we are calculating function value if all the 3 are there. That means 1 1 1. If it 1 1 0, then we can eliminate x3. Only first 2 will give us the answer. That is the way to get the things. And then people compare both the approaches, and both have certain kind of advantages and disadvantages. Okay, so SHAP has a consistency, whereas Lime has some kind of variance there. Here they assume that local model is a linear model. Here they are talking about what are the impacts of each combinations and all that. So since we are talking about the combinations, it's a time taken is more. So if the data is less, then it is very good. That means features are less. But if features are more, then we can go for Lime, because of its because SHAP has a lot of combinations which take a lot of time and all that. These two techniques are model independent techniques, because you can see here in both the approaches, what are the decisions taken by model. They are not it hardly take any, I mean, their solutions, they will not a model dependent. They are independent of whatever the model which we are using. They are model specific technique like tree interpretations. So if you are using a decision tree, this is model based. So if you are using ensemble and all those things, you know that okay, what is the decision at every node. So you are here, and then at this node there is the bifurcation. So why the bifurcation? We know that what is the, if my blood pressure is more than this value, okay, go to the left. If it is less than this value, go to the right, and likewise. So these are model specific. You cannot apply this kind of interpretation in other ones. And since this is simple, this is a simple model, So then there is no need to make a further another simple model to implement or these simple models to understand what is the solutions and likewise. There is another one. This is Slime. It's a basically more of an optimization model. I think I have put one example here. So we try to optimize near around the solution. Let's see what we are doing here. It's a simple model, but it is again it model dependency towards that one. So we want to predict again very simple one like high risk, low risk, and we have three features x1 and x2, x3. X1 is binary, like 1 or 0, smoke or no smoke. X2 is blood pressure level, okay, and then x3 is exercising regularly or not. So the value is basically function we can learn by using some kind of this model, like sign of this kind of equation, because if you put it here, okay, so how we do it, we give some 3 points for smoking, we go 2 points for high blood pressure, and -1 point for regular exercise. Now these 3 points, 3, 2, -1, and then threshold is -3. These comes from various way. These values you can add by various ways. One of the ways, you take the inputs from an expert. That expert will tell that smoking is supposed to be higher. You put it that one, and then he'll say now high blood pressure you keep the second, and then if the person is doing regular exercise you can give negative because it will not lead to a kind of a stroke because it's good practice. And so then you have this kind of a setup there, and if this is the setup, then you can check it whether this one is working fine or not. Yeah, here I'm taking a linear relationship. Here I'm taking a kind of a linear relation, but I'm putting a sign over it. So when you relationship is there, but when I'm putting a non-linear function over it, it become a binary. It's become non-linear. You can make it a complex one just to understand it how it's working. I'm taking simple examples. Okay, so now then you check these points and then verify it. The other way is okay, you take the data which are available to you and develop a model there. And then once you have this model there, then go here. And this is the equation which we use it. Okay, so there is a loss and there is a weighted two parameters. So one is weighted parameter, which is a non-zero weights, and these are the basically how many weights are there, and we try to minimize this whole structure to give an explanation, because those weighted values, those weights, those known weights, whatever the value appear there, that will give us the indication or importance of the features there. But this one is why we put it that model dependent, because whatever we are using here, it depends upon how the model is being used here. If this one is a neural network, then the things will change here. If it is something else, then the things will change here. But it's a one form of explanation of those things there. There is another one which is known as a deep lift, mainly for neural networks and all that. And what they try to do, if I put it here, sorry, I have not put the mathematics. They try to find out, once this one is done, they try to find out the relations and the movement of the weights. They try to observe this, and this algorithm try to observe the movement and the weights between the connection. And based upon that, it try to find out what is more meaningful. It is similar kind of stuff. We can correlate it to like when we go for sparse networks. So we have a fully connected network, and then after training, we'll find that we put a threshold, and if the value of the weights is less than that threshold, we can remove those connections, and likewise. So that kind of a thought is being used here, that which connection is more important in taking a decision. Okay, so there are counterfactual explanation, and the explanations is basically come out when the when we do the changes. These comes after the model is being developed and everything, and then the experts, they check it. So we have one model, we have certain kind of interpretations, but when we work on the actual one, and then we use model as well as at the same time the expert is also working. So then they put some change in the decision, and then we take that why that change make a change in the feature value changes the decision output decision in a much bigger way, and then try to find out the answer, and then we modify our models, or then we label our models that this feature is important in this manner. Likewise, like there are the layer relevance, which I already explained to you. Like an image is there, we take certain features and then we make heat maps, or we go for a pixel wise explanation, that what are those pixels which are important in making this decision. So those are at the layer level. So you can see here what we are doing is, on the concept side I'm talking about, we are looking at the weights, or we are looking at each layer, what is the value coming, and based upon that we can understand that why the model is taking this decision like this, why this heat map and this heat map generated, why this picture is taken as a bus picture, or why this picture is recognized as a cat picture. What are those important zone or features that will help us in taking these decisions? There are various case studies people have implemented. So what they have taken real health care problems, and then get the data, train the models, and then apply explainable models, and then try to give the answers. So this one is a when you try to run with the Lime, you can, and the model is, so the problem is here. Okay, you can say this one is the diabetes data set available on UCI, 17 attributes, 520 incidents or instances, sorry, and then various different models are taken, like random forest. So when you run Lime, this one is a Lime structure. If you use the already built algorithm, so it will tell you that which features are important and why the decision is like this. If it is gradient boost, you can have another model, then you can have a different kind of impact, positive impact and the negative impact. And then you can use shape. Shape is basically, it will give you yeah, I'll come to that one. Interesting questions are coming. So it give you the directions that which feature is important and how much is the impact, like that. So like random forest, the distribution, the impactness is there, impact on the model, these are the features there. So random forest and gradient boost. So this is one case study. Another case study of the risk management, the same kind of structure. So here you will get the value also, the positive impact, the negative impact, and all that. Here you will get kind of a distribution, that the spread, that is how much is the impact from 0 to high value, and both on both the sides, positive side as well as the negative side. So I'm just explaining one of the work which was presented, and you can check this article. This one is basically the lower limb surface EMG measurement, and then explanation or activity recognition. So what we have done is, we have a lower limb and we put sensors. These sensors have surface EMG sensors, which give us the information of the muscle signals, and then muscle signals, they are processed. After process, like we have done the WDEMD, and then we extract features, and after the extraction of the features, what we have done, there are various things you can do. One way is, we have published article on both the sides. So you once you have features, and then what you can do is you use machine learning algorithm, and then you use explainable AI, why this thing is coming. The another one is uh, another technique you can use it. You have many features, and then you have predictions, and then you use explainable AI to find it out what are the more meaningful features, and then you can reduce the features and likewise. So either way we have done these works, and you can see that the model is here, so not jumping. So what is the, that means the RMS value of the signal is the most important, which is helping is making this decision that the person is not jumping. Okay, so not sit-ups means for the sit-ups, what are the main features? That's the mean value and all these things. If it is no staircase or stairs up or stairs down, what is that feature which is playing a big role? So those things you can see here, the LIME is being used to understand the impact of the feature, and that feature is extracted from the signals which we have received on various activities. And if this feature is high means this feature, or you can say, take the simple one, if this feature is highest, that is the mean value of the score is highest, that means the person is doing sit-ups. So we can recognize the activity that yes, the person is doing the sit-ups. Or we can say that based upon this we can say why my machine learning algorithm is saying that this type of the EMG signal is responsible for the sit-ups. So that is how you can do all these things. And this one is another work which is basically done for the chronic kidney disease prediction. Okay, so again, it's a model and the same way of doing the things, that you apply machine learning and then you apply uh, LIME or SHAP to understand that which feature is more important to make a decision there. There are limitations. Now I'll keep 5 minutes for a discussion. Yeah, I crossed the time, sorry. So limitations are most model analysis stage to find the important of the features. So they interact between, try to find out these things, but the interaction between the features, we need to observe that one, because that is also very important. Okay. And then there are other domains we need to see, that if this how important this analysis can help us in understanding those things. Can, like, identification of the models, or can it help us in pre-processing? So pre-processing, sometimes you can see here it, like when we go for dimension reductions and all these things. But if we go for reduction by analyzing the features, that make us more meaningful. Sometimes we do it just by using a statistical method. So those kind of conflicts, those kind of thoughts on the both the sides, they are coming up. Sometimes we remove the features and then we process. So only on those parameters we can comment that which is important, but it may be possible that the features which are removed may be more effectful, and likewise. These are the few references which we have used here. And now I'll take your questions. I can see there are questions from some few participants here, so I stop sharing it. And yes, now I'll check. Either I'm open for the questions. So what you can do is you can write the questions in the chat box, or you unmute and then raise your question. So one question is there from Preeti, that perturbation. What does perturbation means? I think I have make that clear at that time, that what is a perturbation means a small change in that location. Location means if it is a 2 dimensions, so I vary one of the features a bit, so the new feature will appear there, and then we try to see the effect. What is the effect of that one? Okay. Yeah. So you are true that surrogate modeling, because it reduces the complexity of the model, and that is basically the surrogacy we are looking for. That the actual meaning is surrogate is the thought, the hypothesis we put in, and we are not able to solve that hypothesis by the same way. Then what we do is we modify the model near around to solve in that way. That is basically, that is known as surrogacy or surrogate models. So like, okay, I develop a model where a very simple example, I'm looking for a derivative, and now if I get a new thing there in my model, if I had something which is non-differentiable, and that stops my working. So what we will do is we convert that new uh, part which is added, which is non-differentiable, to near around differentiable, so that we can go by the same approach. That is basically kind known as surrogacy, and that these kind of approach are being used here. Okay, I have taken this one. In CNN, with pooling done in immediate layers, how can heat map for pixels can be derived? Yeah, so we interpret there itself. We know that how the pooling is done. We know the scores there, pooling scores, and based upon that, if we can interpret there itself. Okay, so just you assume that if you are doing the pooling, and and if the your before pulling and after pulling, if your image is same, let's take it that way, so how it look like. But if I am doing some operation there, forget about pulling. If I have a image, and if I reduce the size of image, so what I'm doing there, I'm doing some operations on it. I know what the operation I'm doing, and then after doing that operation, what I'm receiving, can I generate it, can I see the heat, can I see the pixel values and all those things, and then can I relate what is the impact of that transformations I'm doing. So it's basically a transformations in all of this machine learning and all these things. Usually what we are doing some kind of a transformations to make complex things to a small things, in particular in feature engineering. So we use transformation. So what is the impact there? And if I know that transformation mathematics or the equation there, then I can give an impact. What is the impact there? The ultimate goal of explainable AI is to study the impact of the features, basically. Okay, I have worked on using gyro and accelerometer for detecting walking, sitting, running, but the challenge is some activities like sitting, lying, dying, are very similar. Yeah, so that is what I'm saying here. Here, if we look for interrelations, interfeature relations, and if our placement of the sensors and the type of sensors, if they are good, they are so sensitive in a way that they can give us the interrelations of the muscle activities or the features which I'm using to develop my algorithm, then probably we can go for better accuracies, because we know that in human body is the most complex structure, and then inside it, for a particular job, there are at a time there are hundreds of other muscles are participating. So how they are contributing, those things are a complex things there. So if I move into that, either in that level, or I use certain kind of a most appropriate uh, approach or transformation, like people nowadays are using, they are working like in neural network. What they are doing, I'm just sharing a very simple example. Say I'm working on the kinematic of a person, the how person is moving, gait of a movement of a person. So I have some signals, I'm using some kind of a gyros and all that, and now I'm training a neural network. But on the training of neural network, big neural network, I'm putting a physics of a person also into that network, and then I'm taking certain decision, then probably I'm getting better accuracy. That I'm answering to your last question. So that is how people are trying to modify, because the physics is also involved there along with the data. So it's a combination of both the two. And then we probably, after we have good accuracy, then we can use some kind of a explanation method that why this kind of a answer is coming if I pass this type of the data to this. Hope I'm able to answer your query here. Any more questions? Any more questions if you have? Then you can put it in the chat box. If you have any question or if you want to discuss anything related to this, you're most welcome. Okay, so no more questions. I think Dr. Surender, we can.
Yes, sir. There is no more
We can-
question on this topic.
Yeah,
So
we can close this part, and then after 10 minutes, can we start? Or
yes,
I
yes,
can,
sir. If you're after 10 minutes, we will join back.
Okay. Okay, then thank you. Thank
Okay,
you very
so
much. Thank you. Okay,
participants-
Dr. Vikas is there. Sorry, Dr. Vikas, I think personally I'm not. We
So
haven't met.
we have met, sir, but in the initial days when I joined,
Oh, okay, okay. Anyway,
we played
okay.
cricket actually initially.
Okay, okay. Okay. In the ground we met.
Yes,
Okay.
yes, yes,
Yeah,
sir.
yeah,
Yes.
but not on another another platform as such.
Sometimes in
Anyway,
front of.
nice to meet you, Dr. Vikas. Nice to meet you.
Yes, sir. Same here, sir. So participants, we will be joining back at 6:30. So the next session will be taken by Rajesh sir itself. So meanwhile, you may have your tea or any snacks you want.
So Dr. Vikas, 6:30 means what time? 6:30 means how much time? Because it's a time difference. So how much
We are
after 10 minutes?
Yes, yes, sir. You can join back after 10 minutes, sir.
Okay, I'll join at
Okay, sir. You are there, na? Okay, I
Yeah.
forgot. Yes, sir.
It's a
So-
time difference of 3:30, 3 hours and 30 minutes. So that's why
sorry,
I'm
sir.
asking. Yeah.
Actually, yes. After 10 minutes.
Okay, I'll join at 3. That way makes your place 6:30.
Okay, okay, sir.
Okay, fine. Thank you.
Thank
Dr.
you, sir.
Vikas. Thank you.